predicting precipitates. So you could be looking for something really bad in the environment or in monitoring an industrial process of some sort or other. And if you know what's there, thank you, if you know what's there, you can predict whether you're going to make a solid or not. Kind of useful. I mean, especially if you're trying to make something, you don't want solids to be gunking up your machine. On the other hand, maybe you do want to make a solid. And if there's any chromium there, you want to precipitate it out of the solution and clean up the environment. So that's kind of where we're at today, is seeing how to predict whether a precipitate's going to form or not. Okay. So Monica, we have ionic compounds. Ionic compounds had a cation, right, and an anion. They're stuck together. Which one's a cation? He's always written first or second? First. And he had a positive or negative charge? Positive, exactly. So there's the cations, there's the anion. Right. So there's some cations, though, Caroline, where they could never, ever form a solid. Never, ever form a precipitate. What cations were they? Where's Caroline? I'm picking on Caroline. Caroline. Why am I going to Victoria? Caroline. Cations. Yeah, cations that can never, ever form a precipitate. What do you remember? Group 1s. Sodium, lithium, potassium. Now this stuff is going to be useful because the very first step in these, well, you can see in the game plan, we're writing a KSP reaction. So you can rule out this stuff. You're never, ever going to form a precipitate with sodium, lithium, or potassium as a cation. Now there's one anion, Jessica, that you will never, ever form a precipitate with. Can you guess what it is? Starts with an N. It's polyatomic. Has a -1 charge. Nitrate. So you'll never form a precipitate with nitrate as the anion. Okay, this idea of forming precipitates and solids, let's take a look at an animation of it. Lauren, what two solutions would you like to try to mix here? The first two are fine, she says. Fine. This one and that one. So, Victoria, will we get a precipitate? Now, to answer this question, to cut you off a little bit, before we always had the what rules, and I gave you this sheet. What were they called? The solubility rules, right? I'm not giving you that sheet, Albert. Instead, I'm giving you this big table of KSPs. Kind of makes a little more sense, because if something doesn't have a KSP, it's not going to be, you can't make a solid out of it, right? So you don't have a table of, oh yeah, you do. Now you do. Oh, hold it. You don't even need it after what I just told you, right? What possible precipitate, Albert, could you form? Remember those two guiding principles of what can never form a precipitate. There's only one possibility here. What could it be? No, you have to combine a cation from one, or an anion, right? Take one from each. Now back up a little bit. It says big M something. That means whatever that solution is, you can never make it. It's never going to be a precipitate, right? Big M silver nitrate. This can't be a precipitate. It's already a solution. It has a concentration. There's so many moles per liter. So these cannot be your answers, NaCl or AgNO3. Does anyone see what it is? Has to be what? Has to be AgCl. Why? Because it can't be the Na. That means it has to be the Cl. And it can't be the nitrates. It has to be the silver. There it is, silver chloride. So the guess would be yes. and it would be silver chloride. Okay, so you dump them together, and they're going to try to show you what it looks like here at the atomic level. So sodium ions are goldish colored, chloride anions are green, silver's kind of silver, and you have the big nitrates. So the solid is forming here at the bottom. Now what they're going to really get into class about is you're not always going to make these precipitates. If I could rewind that darn thing, yeah, do it all again. Yeah. Okay. If there aren't enough ions in solution, if these concentrations aren't high enough, you're not going to get any of these solids. It'll look just like, if I could pause it, I wish I could. You wouldn't get any solids to form. If there aren't enough ions in solution, if they're not concentrated enough, you're not going to get a solid. Now, in this case, there was. You know, you're getting a solid, so those concentrations were high enough. But that's not always the case. And since that's not always the case, we're asked questions like this. Right? If we mix two solutions, molarity this, molarity that, do you expect a precipitate to form? Because if the concentration of the ions aren't large enough, you're not going to form a precipitate. Okay? There's some threshold. And we have to figure out if we met that threshold. So here's the game plan. Here's the solution. We're going to write the KSP reaction for the plausible precipitate, right? You kind of look at the two compounds that they're giving you the solution of. Okay, maybe I can form this solid. So you pick out what it is, and then you write its KSP reaction. Okay? So you figure out what the solid is, most likely is, and remember you can't form solids with what again? Never pick what for solids? Group 1 and nitrate. Don't include those. Okay. And then you calculate a QC, a reaction quotient. Remember, we calculated reaction quotients. Dang, that's a long time ago. Do you remember anything like that? QC. What do we use it for? It is. It's just products over reactants. It's just like a trial equilibrium constant, kind of, right? And we use it to predict whether we were at equilibrium or not. And if we weren't at equilibrium, we use it to predict whether we're going to shift towards reactants or products. That's what we use it for. Here we're going to use it to predict if we have a precipitate or not. So you go ahead and you write the KSP reaction, and then you write the KSP expression, but we shouldn't call it KSP because we don't know. Call it QC. So products over reactants. So you'd have B to the little b and C to the little c all over 1 because you have a solid. And then you just plug it in because they gave you the concentrations. So when you plug this stuff in, you get a number. Now you just get a number. And then you compare it to KSP. It has to be one of these cases. Either you're going to nail the KSP, or it's going to be smaller, or it's going to be bigger. It has to be. Okay? Where do you get the KSP from? Table. You don't memorize that stuff. Table. Yeah. Okay. So let's say, Eric, let's do this one last. Let's do this one first. You calculate your QC, and it's too small. It's smaller than the KSP. Would you expect a precipitate? He says no. He's right, but why? It's easier to conceptualize it than to memorize it. If QC is too small, Q's are products over reactants. That means you don't have enough product. You don't have enough ions. You don't have enough ions floating around. They're not going to stick together because you don't have enough of them. So no, you're not going to form precipitate. QC is bigger than KSP. Now you have too much. What? Too much product, too many ions. They're going to form precipitate. It has to. So yes, you will form a precipitate. You get the KSP number. Exact same number as what's in the table. I left this one for last because you could argue either way. You could argue, yes, I expect to precipitate, or you could argue, no, you don't expect to precipitate. Yes, because get a microscope out and find the damn little crystal floating around in there, right? Because you hit the KSP, you're right at the brink. Or in lab, if you haven't had, have you had lab yet? Okay, lab tomorrow. Some people have had lab. There is this jug of calcium hydroxide, and there's a solid calcium hydroxide on the bottom, so it's saturated. It has reached the KSP. So what they do, but what you have to do is you have to pour some of it off through some filter paper, and you get this nice clear solution. It's still saturated with calcium hydroxide. It's reached the KSP, but it's nice and clear. So you can argue either way. You can filter out all that solid. So that's why this one, I think the book probably wants you to say yes, but I say you can argue either way. Okay. Now before you move on, let's say KSP, just to give you a trial of this, 8 times 10 to the negative 7. Give me a number, Alyssa, that is less than 8 times 10 to the negative 7. I want a QC, why isn't it writing? I want a QC that is less than KSP. Any number. 7 times 10 to the negative 9. Agree? The important part, yeah, this is important, but this is where you're going to be looking every single time, that exponent, right? 10 to the negative, anything, 10 to the negative 8, 10 to the negative 9, 10 to, that's all smaller, right? It's just the opposite of what positive exponents. Okay. So that's our game plan. Now this first one isn't too bad. The second one is a job. So I think we should just stay where we're at instead of going to the boards, because the second one's kind of a job. Let's try this. From each of the following ion concentrations in a solution, predict whether a precipitate will form in the solution. Okay, Maria. What would you do first for this? Set up the QC. Okay, but to set up the QC, I think you should write a what first? Yeah. Equation, the R word. Reaction, right? Because the reason why I don't want you to jump right to QC expression, you're going to forget to square something. You're going to, right? It's way too easy to do that. So I strongly suggest writing the KSP reaction, because it tells you exactly, because everything's organized there. There's no memorizing. You just figure out what the solid is, put it there, and then break it up into its ions. So what would be the solid, Summer? She said PbCl2. Do you agree? Jasmine, where's that 2 coming from? The Pb2 plus. She's right on. You guys are on track here, right? Remember doing this? This charge ends up going there, and this charge ends up going down there, right? Okay, PbCl2. It's going to break up into, Monica, what and what?
Pb plus 2Cl.
Pb plus 2 and Cl negative. Good. Right? Write the expression, Caroline. They wanted to write the QC expression. To be technically correct, you'd write what? Okay. Uh-huh. Yeah. Okay. This step, man, especially in the homework you just got done doing, I can keep as many stars as I can. I can't underemphasize how important that is. Here you could probably skip it, I don't know, but especially the last homework. If you skipped writing this KSP expressions, man, I think you screwed up 5 times out of 10 probably. That's the way it seems like doing the homework and stuff. Okay, plug stuff in directly. I get, what, 0.035. And then take that times 0.15, but I got to square it. What is it? 0.035 times 0.15, got to square it. 7.9 probably times 10 to the negative 4. Okay. Well, we're supposed to compare that, Monica, to KSP. We need KSP for lead chloride. What's KSP? 1.6 times 10 to the negative 5th. That's the KSP. So, Jessica, will a precipitate form? QC is lower than KSP, or QC is bigger than KSP. QC is bigger. Then we have too many ions. Make a precipitate, right? Yes. Expect a precipitate. Okay. Let's try this next one. Okay, Lauren. A 45 ml sample of 0.015 molar barium chloride added to a beaker with 75 mils of 0.0025 molar potassium chloride. Will a precipitate form? What should we do first? Hey, is this a solubility problem? How can you tell? Because the exam that's coming up, you have all these problems mixed together, right? How do you know not to do ice? Right? Because I'm always doing ice. But all of a sudden today, you notice? Stopped completely. How could you read this, Lauren, and say, don't do ice? Slap Albert on his wrist and say, Albert, stop doing ice. There's got to be a way to tell. Yeah, there's one point. It's asking for a precipitate. But what was the solubility? The whole purpose of doing ice had something to do with solubility. Either they were asking you for solubility, or they were giving you solubility. Regardless, it was a solubility problem. They had the word solubility in there. This isn't. So you don't do ice. Okay. So if you're not going to do ice, Victoria, what should we do? Put a reaction. So what reaction? Write the proposed or what you think is going to be the, which one? Not Ka, not Kb, KSP. Write a proposed KSP reaction. Well, if we're going to write, Albert, a KSP reaction, we need a solid. What solid do you propose that we form? BaF2. How did he come up with that? Yeah, because the BA has a +2. The fluorine has a -1. Good. So the formula looks right. Because what's your other choice? If you don't pick BAF2, the other choice is KCl, and that can't work. All right? KCl can't work because you have K in there. So this is your only choice. Okay. Ramiro, that breaks up into what and what? Yeah. Okay. And then you probably do what, Eric? Calculate the QC, products over reactants. Right? So Alyssa, what was I complaining about? Right? I was saying, oh, this is going to be a hard question. Right? See what I'm saying? Because what's in brackets has to be what units? Molarity. Didn't they give us it to us? Didn't they give it to us? But we added some milliliters to it, right? If they would have just stuck with the 45 mils and don't add anything to it, the concentration of barium would have been 0.0015. But they dumped in 75 mils. So this is messed up now. They dumped in, right? They diluted it is what they did. So that concentration of barium, it's going to be bigger or smaller than 0.0015. It's going to be smaller. Because now it's not going to be quite half, but it's going to be smaller. So just like the fluoride, too, its concentration isn't going to be 0.025. It's going to be smaller. You've added 45 mils. All right, Maria, we need some game plan on how to get these. How would you get the concentration of barium? No, ice table's not going to help. Ooh, did you hear Maria? I like her game plan. Did you hear what she said? The moles all over the total liters. Okay. But we don't need to calculate an equivalence point. So we're not going to do this whole big, long thing that involves mole bridges and stuff. How will you get the total liters in this case? It's so much better, Summer. How are you going to get the total liters? Yeah. So what two numbers would you add up? Or what would you add up? How would you get this? Yeah. The 45 milliliters and the 75 milliliters. Right. And then, but convert them into liters. So what is that? 1,000 mils in a liter? We got the bottom part. So much easier than before. We had to go through that whole big long calculation to get the equivalence point. But this isn't a titration. This is just dumping two solutions together and predicting whether you get a solid or not. So we've got the total liters. Jasmine, how do you get the moles of the barium? Right? Okay. Okay. All right. She says use the big M. Big M. Okay, keep going. You're on track here. That's going to be what over what? Yeah. Moles. All right, it's right here. Ah. All right. Do you remember doing this? How are you going to solve for moles here? What equation, Monica, are you going to set up to solve for moles? 0.0015
times
Oh, let's just set up in the equation. You're right. But
equals moles.
equals moles all over.
Will we cut the total? No.
Ooh, there's two possibilities here. Do you use the total volume or do you use the 45 mils?
45 mils.
The 45 mils, because you're just after the moles of the barium, and you took 45 mils of that solution. But it has to be in liters, though. Okay. But I don't know if you heard Monica. She's right. You got to multiply the 0.0015 times the 0.045, and you'll get the moles. .75 times 10 to the. Okay. That work, Maria? 6.75 to 10 to the negative 5 is the moles. So that's what we put in up top. So we can finally get our concentration of barium. It's going to be 6.75 times 10 to the negative 5 divided by, what was that? 0.12. So about 5.63 or so. 5.625 if you want to write all the digits times 10 to the negative 4. There's our barium. You have to do pretty much the same thing to get the fluoride, yeah. But at least we know this one. This one is 5.625 times 10 to the negative 4. So get the fluoride now. Get the fluoride concentration. Put it in. Get your QC and predict whether you're going to get a precipitate or not. Lost, man. That was a good time to ask. Oh, we need the KSP, don't we? For barium fluoride. 1 times 10 to the negative 6 is our KSP. Thank you. So see if you can get a QC and compare it to that. Yeah, and I can do the exact same thing for the F. And don't forget your exponent. This is times 10 to the negative 4. All right. So QC doesn't equal this. That's barium equals that. Barium is moles over total volume. Jasmine, did you get a number for the fluoride? fluoride? Did you get a fluoride?
Yeah.
5.6 times 10 to the negative 3. Let's see if anyone else got that. Whoa, fluoride. Did anybody get 1.56 times 10 to the negative 3 for fluoride? Now you're going to have to square it, but... Okay, several folks did. So you should square the fluoride, multiply it times the barium concentration, compare it to KSP, see what you get. For fluoride? Oh, did you convert milliliters to liters? You get 10 to the negative 3? Everyone's getting 10 to the negative 3, Eric. Okay, so folks are getting, as your final QC, what did you guys get as your QC? Okay. Anybody else get that? 1.37 10 to the negative 9? Okay. A lot of folks are getting this. So make sure you're getting these numbers, right, for your fluoride, for your barium, for your QC. And then, yeah, Summer looked up the KSP. She said it's 1 times 10 to the negative 6. So that means yay or nay for precipitate. Yeah, no, because it's too small, not enough ions. Okay. Okay. QC folks got about 1.4 times 10 to the negative 9 for your QC. All right, try this one then. If you got it, try this one. If you didn't get the previous one, just ask so I can help you out. Should be able to knock this one out. So will a precipitate form? Not an ice problem. Not a solubility problem. What's solid going to be? Oh, you put the 2 in the wrong place, right? Go from this guy. The 2 means that he has to be a plus 2. Yeah. So you're on the right track if you picked what as your solid? PbCl2. Good. For lead chloride, 1.6 times 10 negative 5 is the KSP. Let's see if we can get some consensus. Ramiro, did you get any of these? What did you get for your lead? 6.2 times 10 to the negative 3. Anybody else get that? Okay, Eric got it. Maria, what did you get for your chloride? 1.3 times 10 to the negative 2. Is that good? Should be able to get a... Lauren, did you get a QC? You started it? Oh, okay. Did you get a QC? Okay, you're almost there. QC is 1.1 times 10 to the negative 6. Yeah. Okay, several folks got that. Okay, so that would mean yay or nay on the precipitate. It's smaller. That's right. QC is smaller, so not enough ions, so no precipitate. No solid. Right? So we're about out of time, but come by and work with this stuff with you, and it's not so bad.